Okay, how's the sound in the back? Is it okay? All right. Yes, so hello, thanks to the organizers for letting me speak about this. I'm just going to jump right in. So first of all, I'm part of the an Australian Research Council Centre of Excellence, which is the Centre for Quantum Computation and Communication Technology. And it's an international team working to develop technology for universal quantum computing and secure quantum communication. We've got over 200 researchers across 7 Australian universities, and we have 25 formal partners internationally and 22 coordinated research programs. I'm from RMIT University, which is a university in Melbourne. RMIT is no longer an initialism for anything. It's although I like to think of it as the Royal MIT as opposed to the non-Royal. Anyway, so this is my group. This is what we call it Kermit, QURMIT. So feel free to check this out, kermit.org. Okay, so I want to start with a fundamental question that sometimes people who work with qubits would ask, which is, why are you bothering with continuous variable systems? Now, maybe this isn't asked so much anymore, but I think it's worth revisiting nonetheless. So I just realized I should probably start a timer. So first of all, some of the advantages of CV systems, at least in optics. If you compare continuous variable approaches in optics, which is where I got my beginning, although I understand that there's a lot of work being done in superconducting circuits at the moment. In optics, we have deterministic entanglement, and that's a big deal because for many years in optics, the qubits were single photons, either in one mode or in another mode, and that's your 0 or your 1. So you have a single photon either here or there. Or in other words, you have states 0, 1 and 1, 0 in the number basis as your qubits. And it was very hard to get them to talk to each other. The best gates that were available involved ancilla photons and measurements, and they only worked some small fraction of the time. So that was a big problem. So if you work in the continuous variable regime, you use the whole Hilbert space, or at least a large portion of it, you actually have deterministic entanglement. So that's a big deal. The other thing is that there's some immensely scalable hardware that you can make. So Wari gave a nice description of that earlier today. I've been working with the University of Tokyo on their designs for some years now, more than 10. And so we have, it's possible to make very, very large resource states for quantum computing with relatively small experiments. Now I say relatively small because I'm sure that Wari and company may not find them to be too small, but still they can fit within a laboratory. Room temperature operation, that's certainly true. And that's a big advantage for a lot of what's happening in optics. Now in circuit QED, turns out that these microwave cavities are less noisy than the transmons. So if you use the microwave cavities as the information carriers and the transmons as ancillas, you can actually do better in terms of lifetime. At the fundamental level, we avoid premature optimization. So like in optics, why should we restrict to photonic qubits, single photon qubits? Single photon is just some wave function. I mean, maybe there's a good reason for it if you have certain hardware that produces single photons, but most hardware doesn't produce just a single photon. And if you think it does, that's probably because you're not thinking about how you know that it's produced a single photon. So there's all sorts of heralding and all sorts of problems. I mean, usually we produce Gaussian things. Now, if you're taking a photo of the slide, I might encourage you to wait because there's one more. Both together, there's more options for practical tasks. Such as quantum cryptography and cluster states. In another version of this talk, I talk about cluster states a lot more. And there's also hybrid schemes. So continuous variable technology helps to manipulate photonic quantum states. Now, there's some disadvantages, and there's going to be 3 of these as well. So if you want to take a photo, you can wait until they're all done. At the practical level, there are imperfections due to finite energy. And this is a big one because the way that we naturally think about the continuous variable Hilbert space, you can think about it in the Fock basis, sure, but then that's a discrete Hilbert space. It's just countably infinite. But if you think about it as a continuous variable system, the quote, computational basis has a continuous spectrum. And that's a bit of a problem because the eigenstates of that spectrum are not technically in the Hilbert space, although you can get very, very thin normalizable states that are in the Hilbert space, and those are squeeze states. And so we treat these delta function normalized states as if they were real states. But there's some funny business going on. And mathematicians care about this. And there's lots of things that are fundamentally at the mathematical level, at the rigorous level, impossible with infinite but possible with arbitrarily large but finite. I have a hypothesis that none of those actually matter physically, but I don't know if that's true. Anyway, you do have to take into account the fact that you'll never make a perfect state, even in principle, even with perfect experimental equipment, you will never make an ideal position eigenstate, let's say. So you eventually have to discretize for error correction. So you can't use the continuum literally. It's like analog computing. You need some discreteness for error correction. At the fundamental level, there's more questions to answer. For instance, what discretization should we use? And we have to incorporate the effects of noise from day one. And this is complicated. It's easy to end up writing a crap paper if you don't bother to think about that. Now, that doesn't mean that you have to do all the analysis at all levels and in depth to write a publishable paper, especially if it's some new idea. But it just means that you need to be aware of where the idealizations are and at least make some attempt to discuss what it will be in reality. Now, both together, we have to do extra work to employ existing algorithms. And that's because we have CV hardware, as it were. There's a smaller literature. There's fewer optimized experimental platforms. And that's that. So let's talk about encoding qubits into a mode. So we've seen a number of talks on this paper. Here's an approximate GKP state. We've got, I don't need to go into this too much, but we've got, this is the wave function representation. If you ever put a photo like this in front of a lot of experimentalists, you got to make it clear this is not a frequency comb, and it's not a mode-locked laser. It's actually the wave function of a single mode. I know you laugh, but it's actually a big complication. This is the wave function of a single mode. So I like to talk about it as if you have a peak here, this would just be a squeeze state. The vacuum is something like that. If you have this peak, it's just a squeeze state. If you have these two peaks, that's a squeezed cat state in the wave function picture. So this is a squeezed multi-cat state, or in Japanese, a squeezed maruchi neko jotai. Okay, anyway, moving on. So the blue spikes represent an approximation to the 0 state, and the red spikes represent an approximation to the 1 state. And so this would be some approximation to the plus state. Now there's this big envelope here, so anyway, we'll talk about the effects of that. I want to talk about how we would correct errors with these. Most people know, but I'll do it anyway. So this is a crappier version of some state that's mostly 0 plus a little bit 1. And it's encoded, we have 0 plus 1 with some errors encoded here. Now, my circuits go in the correct direction, which is right to left. And I encourage everyone to adopt this. And if you're interested in why, I have an actual aside as to why. But I find this, now that I'm educating other students, I find this infinitely better than left to right. I know that left to right is ingrained, and it won out in the wars of circuit direction in the early days of quantum information. But I think we need to correct it because there's a number of advantages to this. So what we have is these are the input states on the right. All the gates mean the same thing. They're just written in the other order. The input states on the right, and we have a logical state here. We do some entangling operation, and we make a measurement. Notice that measurements are just bras. And in fact, you can calculate this amplitude just by dropping the wires, replacing the gates by their operators, and just do the calculation. There's no reordering. There's no weird combination crap that goes on. There's no weird symbols for measurements. It's just that. Anyway, I'll get off my soapbox, and you can ask me more later if you're interested. But there's many advantages, especially for those of you who are educating others. Anyway, so what happens is you get an outcome, and you get a better state. The outcome helps you figure out how to fix the state so that it's back on grid, as it were. So it ends up a little bit off grid, and the outcome helps you figure out how to move it back. But you may get it right, and you may get it wrong. And you hope that you get it right, and that hope comes about by some educated guess, some information about the noise model. Generally, you move it back toward in whichever direction it requires a smaller shift, although that's not always the case in multimode codes. All right, but a better question is, why are we using GKP? So we saw Victor's talk with a lot of different codes. There's some crazy codes these days. Why is GKP and GKP-like codes, why are they favorable? Well, here's a table. Now, don't take a photo of this because this is not the final one. I'll tell you when it's the final one. So you'll have plenty of time. I've done this many times, so I know how this goes. Anyway, in photonic qubits, in other words, single photons in one of two modes, we have these challenges or ways of doing various things. So for universality, you need single and two system Clifford gates, and you need some one system non-Clifford. Now you could talk about it instead as, well, anyway, yeah, that's true. You could, yes, right. And you need to be able to prepare some sort of standard state, and you need to be able to do a measurement. Now, for photonic qubits, the Clifford gates, the single system gates, both Clifford and non-Clifford, are done entirely with passive linear optics. Now, this is a big advantage because it's just pieces of glass and, well, just pieces of glass and partially silvered mirrors. So beam splitters and phase delays. And so that lets you do all single system gates. But to get these qubits to talk to each other, that usually takes post-selection, unless you're going to do something much more complicated with quantum memories or something. But it's challenging. Preparation, spontaneous parametric down conversion, quantum dots, rare earth ions, et cetera, usually heralded SPDC is the way that people are going. And measurement with avalanche photodiode, now it's the equivalent for telecom. So that's relatively easy. The green means easy, the yellow means eh. GKP, all Clifford gates are Gaussian. The non-Clifford gate is, or was, non-Gaussian. We'll get to that in a sec. The preparation is terrible. Squeezed multicat states in optics are terrible. In circuit QED, it can be done. In optics, it's bad because we don't have strong nonlinearity. But there are proposals for doing it. And measurement is homodyne. But the nice thing about this, well, I'll get to it in a second. Right now, the nice thing about this is that the analog of the Clifford group for general CV operations is the Gaussian group. And so this matches up quite nicely. Now, I want you to focus here because in 2019, a group of us showed that this is actually can be done entirely with Gaussian operations. That the vacuum state, for instance, has magic with respect to the GKP encoding. Just like the GKP state has magic with respect to general CV operations, Gaussian operations. And in 2020, these researchers, including Takaya Matsuda, who's now working with me at RMIT, showed that if you go in the other direction, if you make a magic state first, it's actually easier to make the computational basis states afterwards. Anyway, either way, what you have is that, look at this. All of these are either Gaussian. Now, this is the final one. You can take a photo. All of these are Gaussian, and homodyne is the measurement. Except you still have the challenge of the difficult to make squeezed multicat state. But just like with measurement-based quantum computing, where you front load all the difficulty, we're doing the same thing here. We're front loading all the difficulty of making these states. Once you have them, everything else is relatively easy. In fact, with the brief aside, I did some consulting with Xanadu recently in the last couple of years and helped them with their blueprint for their architecture. And their architecture involves making these states non-deterministically and sending them through a linear optics system and doing homodyne measurements. All of the latter, once the states have been created, can be done at room temperature, which is a big advantage. Okay, so let's move on. So these states have been made in trapped ions and also in superconducting circuits. They have not yet been made in optics. So let's talk about the issues, however. This is where we actually get into it. So conceptual issues. The definition of the GKP state differs from how it's used. The GKP state is defined as a comb. It's defined as a delta comb wave function. Those things are very, very not in the Hilbert space. Not just a single delta function, but a comb of delta functions. So the ideal GKP logical subspace is entirely unphysical, infinite energy. And when I say it differs from use, it's because when we talk about the logical subspace, we talk about operations that only affect the particular values of position or momentum. And yet we do operations that involve the entire Hilbert space. We do displacements. So the states that we make are not in the logical subspace, and the operations that we do not limit their action to the logical subspace. They only do when you have a logical state. We bin these measurements of Q or P to get qubit-level Z or X outcomes, and more conceptually problematically, large displacements by a stabilizer create an orthogonal state. So you have an operation that should do nothing to your logical operation, to your logical information, and yet it creates an orthogonal state of the one that you started with. What is going on? So And finally, how does the particular shape of the wave function affect the logical content? We'd like a code that reflects how these states are actually used in practice. We'd like an actual logical qubit, and we'd like to rigorously capture the parts of the state that don't matter, like tiny displacements or overall large displacements by a stabilizer. And we'd like to account for any logical qubit noise due to state imperfections. Enter the modular bosonic subsystem code. This is not the only one I'm going to talk about today, but this is the first one that, I believe the first one that ever came out for this code. So this is by Ben, myself, and first author, Giacomo Pantaleoni. Giacomo is finishing up a postdoc at the University of Sydney soon, and he's on the market. So if you like what you see here, get in contact with me. He's quite brilliant. Anyway, let's get on to it. So basically the idea here is we take the Hilbert space for a CV mode represented by this line here. This is just the real line, it's just position. And we cut up the position basis into what we call even and odd bins. So the even bins are blue and the odd bins are red. And then what we see is if we take these blocks, these little bins, and we snap them all together, and we take the red ones, we snap them all together, we have two copies of the real line. This is the old Hilbert Hotel, where you can always put one more person in a hotel with infinite rooms. So similarly, you can take a copy of the integers, and because integer number of bins, countable number of bins, and divide it up into two copies of the same thing. And so what we have is now a qubit tensor a mode. Now the dynamics, of course, are not going to respect this decomposition, but at the Hilbert space level, there's nothing wrong with it. You can do this. You can just cut it up like this. So we use this to define a logical qubit. And we say that the position operator is some scale times some integer valued bin number plus some remainder, which is a modular variable. We don't need to worry too much about the mathematics. Anyway, pictorially, this is what happens. We take a wave function and we say the parts that are in here correspond to the zero logical wave function. We're just going to cut that out. The parts that are here correspond to the one logical qubit state, and that's the wave function for it. So when we pick them out, what we see is that all the blue parts went down here and all the red parts went down here, and this is our decomposed state. It's the exact same content as the original, but now it's written in this tensor product decomposition. You can do this. The gauge mode, so we call this a gauge mode. This is the extra information we don't care about. I mean, we do because it affects the logical information, but we don't fundamentally care about it. The gauge mode states are slightly different in this case. So that creates entanglement between the logical qubit and the gauge mode. And that creates decoherence. But we have all standard tools of quantum information now available for the analysis of this. This is a non-Markovian model since the bath, this gauge mode, sticks around and re-interacts with the logical state as it evolves. Okay, so some logical equivalences that come out of this are that if you just have, you don't have to have GKP states anymore to get the same logical content. So if you just have a position eigenstate, it's fully within the blue bin, and there's nothing within the red bins, and that turns out to be logically equivalent to a zero state. Momentum eigenstate is logically equivalent to a plus state, but you'll notice that the gauge mode here is not a comb. Anyway, if you have a GKP state, then the gauge mode is also a GKP state, still has the same content, one, same thing. And if you have a superposition of them, like an ideal GKP state, then what you get is the logical state that you've encoded, tensor, a GKP state in the gauge mode. Okay, thanks. If you take the gauge trace of this, you get the same logical content, etc. If you don't, and so this accounts for the fact that you can move by a stabilizer and you almost get the logical state that you want if it's a good encoding. But the problem is that if we have an approximate state with finite squeezing and an envelope, then we get some strange behavior. So we saw that a single spike, 0Q, is a highly pure zero logical. And for high fidelity states, dephasing is the dominant noise. In this decomposition, dephasing is the dominant noise. There's a preferred axis to this decomposition. And this axis depends on our choice of decomposing in Q rather than P. If we had chosen P, we would have dephasing along X instead. So is there a decomposition that has no dephasing? That would be nice. It's kind of weird that we have this noise and this asymmetry here. We know the code is should be symmetric. So a slight detour, subsystem representation of stabilizer codes. This is a very old idea, 96. Andrew Doherty pointed this out to me. Well, to us, to an audience, I was in the audience. Just a bit flip code can be talked about in a subsystem representation. So the bit flip code has 3 bits. Now you can think of this as 3 qubits, and we only care about bit flip errors. That's fine. You can put kets around these things. I've done it classically just to minimize notation. So the 2 logical states are here, 000 and 111. And all of these are errors, but they're all, if there's, anyway, they're errors. So how we group them is important. We take a majority vote to group the error states into what we believe are the corresponding logical states, and that's because of what we believe the noise model is. And we group them together like this. So what we really have are 4 states that represent a logical 0 and 4 states that represent a logical 1. Well, guess what? If you have 4 states, you only need 2 bits to represent it. So this is the hint that says if you have these 8 states, you should be able to decompose it into some logical state and 2 bits of syndrome information. So here and here, the syndromes would be all 0, and then 0, 0, no error. And then there'd be 3 different values of the syndromes that would correspond to the remaining states. So how do you do that? Well, let's go back to this. One thing we might do is just get taking clue from the way that we do the bit flip code is take parity. So we take the parity of the first 2, and we take the parity of the second 2. And now you can stare at this if you want, but just trust me, what I've done, I'll just do an example. Let's take this one. So the first 2 here are odd parity. So this has a 1 in this middle column here, it's P1. The last 2 are even parity because they're the same, and it has a 0 in the 3rd column. The logical bit I have left conceptual because we claim this to be a 1 by a majority vote. So I put that there. But the real question is, what does that mean? So those, okay, there's a separation. But what does this logical bit mean? What is that? If we do what one might do and say, well, the logical Z operator is just Z on the first one. There's nothing wrong with that. Sure, you could do that, Z on the first one. In other words, N1. But if you do that, you get this grouping. And now I'll just highlight what's wrong. These 2 are wrong. What I've done is I've just taken the first bit and said, that's my logical bit. That doesn't work. We know that doesn't work. Those 2 are wrong. If we take the second bit, these 2 are wrong. If you take the 3rd bit alone, these 2 are wrong. There's always 2 that are wrong if you just take 1 bit. And yet we talk about a single Z as being the logical operator. It's not really. How do we fix this? Well, we fix it by looking at what's wrong with those. Well, they're wrong when the syndrome bits are 1, 0. And so what we do is we just add on something that corresponds to that. It says if the first syndrome bit is a 1 and the second one is a 0, hence the bar, we flip the first bit. We can do the same thing with our 2. We just change how we deal with the syndrome bits. There's a 3rd way to do it as well, and that fixes it. But importantly, here's 4 different ways, and there's 3 that are equivalent to this one. There's 4 different ways to define a subsystem view of this code. And they are all based on different decoders. There's a naive decoder based on N1, N2, and N3. That's bad. And then there's the way we actually do it, which uses the syndrome information. Different decoders give rise to different subsystem decompositions. And getting the right logical bit requires a nonlinear operation, this multiplication of the 2. And if we were to do that in quantum circuit, that would be a Toffoli gate, the non-Clifford gate. There's question time, right? Okay, well, I'll go quick. So this is equivalent to majority vote of the outcomes. There's no Clifford circuit that allows you to transform from physical qubits to subsystem decomposed qubits. And so we should look beyond simple basis partitioning to give a useful subsystem decomposition. And this is what some other authors did. So how does this relate to GKP type codes? Well, the decoder corresponding to our subsystem decomposition, the one we came up with, is optimal in Q, but non-optimal in P. I haven't said what it is, but that's a fact because it has the Z-axis dephasing. Can this be fixed? Yes, it can. I'm gonna have to go through this too fast. Take the real line, divide it up into bins. If you have a function on the real line, you have a function on each of these bins. so we can restack them. So we have some remainder, we have some label of the bin, and we have the position. So a function of the position, like a wave function, is really a function of two variables, m and u. So we can write it like this. And then what we can do is we can say for any of these, so pick a particular u, and now I have a wave function on all of this. I pick a particular u, and there is a discrete function on these points. I can take a Fourier series of that and convert that into a continuous function on this interval. And I can do this for all values of u, and thereby create a function on a patch. So instead of a function on the discrete cross interval, we have a function on a patch. So we have this. And this was originally realized in 2016 by a group out of Paris. And this is an approximate GKP state. And then just this year, we had a similar result. I think I'll skip this. But the point here is that we can take the left patch and identify that as our qubit 0. And the right patch is identify that as our qubit 1. But this produces the same problems as before. And that's because of the way that we handled the differences in shifts. If you shift within here, it does nothing. But if you shift here, it rotates the qubit just a little bit. And that's the asymmetry. And that's the logical dephasing. Now, these guys, Mackenzie Shaw, Andrew Doherty, and Arne, came up with a different method to do it. I've just got 2 slides. Okay. So if you rephase the right half of the Zach patch, that's just a different phase convention. That cancels the rotation and fixes it. And with that, I will say, is that what I want to do? I will just highlight the benefits of this. This is symmetric with respect to X and Z, and it corresponds to the correct decoder. And other decoders will induce other subsystem decompositions. So I'll skip to the conclusion here and leave that up and see if there's any questions. Thank you.
Do we have any questions? Okay, so first, very interesting results with the perspective subsystem code. And I wonder, like, if we have a last channel, those the lattice size will shrink. And how should we view, the subsystem degree of freedom?
It's very weird. Yeah, it's very strange. So one of the things that I had to gloss over kind of quickly, because I didn't manage my time well, was this. So displacements will reasonably respect the symmetry, but loss will have a very strange effect because it doesn't reflect this at all. It can be described within the patch, but it'll have some strange effects. That's all.
Yeah, so this, the Zach subsystem decomposition was defined with respect to the standard GKP decoder, the square patch decoder. And as you were talking about for other types of noise like loss, there may be better decoders. And so this would not be the right subsystem decomposition for a different type of noise. That it's kind of based on a noise model, which isn't necessarily the physical one. Sorry.
Well, yeah, that's all right.
But maybe there's still a chance we find a good way to.
Yeah.
There's nothing wrong with this. I mean, this is just a wave function. It's just another way to write a wave function. And all the tools that you use, like amplifying or preamplifying, or using some fake amplification by changing the measurement, rescaling the measurement outcomes after the fact. There's all sorts of tricks you can play to deal with loss. A lot of which you've looked at, some that others have looked at. But exactly how it's represented here, we haven't looked at that. It's an interesting question.
Do we have any other questions?
Is there any way to think about playing around with the gauge mode to, I mean, it's obviously you want to do logical operations on information, but is there any tricks you can play on the gauge mode that might improve things?
Well, maybe. So one thing that we did, so I appreciate you bringing that up, because of these logical equivalences that I talked about, in particular, zero momentum has the same information as plus state, it's possible to replace them. So instead of using the plus GKP, you can use a zero momentum instead. Now, obviously you can't do as well, but in the Xanadu architecture, this is a number of people proposed this, that you don't, if you're going to make a 3D cluster state with GKP states as the source, You don't necessarily need all of them to be the GKP states. As long as most of them are, it's fine. But if you fail to make a GKP state in a given time step, you can replace it with a squeeze state. And a number of us suggested this. My reason for suggesting was their logical equivalence in the subsystem representation. So this is an advantage that Xanadu has over PsiQuantum and similar architectures because this has no holes. So it has regions where the error correction is dodgy, and you're going to have to work with that in your decoder, but it has no holes. You still have all of the connectivity that you want.
Okay, so our next session will begin in 12 minutes. Let's have some clapping for all of our speakers.